Okay, good morning, everyone. Congratulations to those taking the course for graduate credit. You've reached the end of the first 10 assignments. Hopefully you have an experimental platform now on which you can evolve neural controllers for virtual robots inside of virtual environments. Take a deep breath, pat yourself on the back, and around we go again. So for the graduate students, there is now waiting for you the first of the 5 differentiable assignments. I've been working on these. There are not going to be 10. There will be 5 of them. In the first one, you're going to be tackling objects like you tackled links in the first assignment. Next week, you're going to tackle springs. So we're going to attach objects together with springs. This is a little bit different from attaching links together with rotational joints. We're going to connect together mass points, so very small bits of material. We're going to attach them together with springs. The week after that, you're going to be adding motors to the springs. So I want you to imagine 2 small bits of material attached with a spring, and inside the spring is a piston that can pull the pairs of connected objects towards one another, or the piston can extend extensive force and push those pairs of connected objects apart. After that, as usual, after that will be spring recess, and then after that, the 4th assignment, you will be adding sensors to a whole bunch of objects that are connected together with motorized springs that will make this robot start to move. And as always, towards the end, you're going to be connecting those sensors to those motorized springs to get your robot to move. What you should have at the end of this 5th differentiable assignment is a robot that's made up of a bunch of objects connected together with motorized springs that are pulling and pushing pairs of connected objects together. We have actually seen a robot in this class that already looks quite a bit like that. Where and when did we see that robot? Anybody remember? The tensegrity robot. So NASA is actually prototyping this as a potential way to develop rovers for the years to come. That's what you're going to be developing in these differentiable assignments. What do we mean by differentiable assignments? Well, if we go back to our Bratenberg vehicles for a moment, where we've got a small vehicle that's driving around with 2 wheels on the back and 2 sensors on the front, and we have the 2 sensors connected to the 2 motors. This is, as we've seen, sort of the simplest robot you can imagine. In this course, what we're looking at is ways to wrap this whole thing in an evolutionary algorithm, where the evolutionary algorithm in this case is trying to find 2 numbers for these 2 synaptic weights that cause this Bratenberg vehicle to do whatever it is that we want this vehicle to do. In an evolutionary robotics experiment, it's a semi-supervised learning problem. Semi-supervised meaning that we take 2 sets of synaptic weights, drop them onto our robot's neural controller, watch how the robot does it running around, and we get back a single number, which is how well the robot did. How do we determine how to change these 2 synaptic weights to make this number bigger, to make the robot do more phototaxis? Randomly. The short answer is we don't know, so we make random changes. Part of what's going on in the current AI revolution is figuring out how to actually take this number and propagate it backwards from the sensors into the motors and identify it was this one that was wrong, not this one. We can actually, in some cases, localize where the problem was or where the issue was that was causing the inefficiency. And then we can also identify not just where the problem is, but automatically identify how to improve that number. Whatever this synaptic weight is, should we make it a little bigger or a little smaller? Again, usually we don't know, so we do it at random. When we design robots in a differentiable manner, we can actually apply some of this machine learning machinery to actually identify where the problem is and fix it automatically and remove the randomness from the way in which we automatically design autonomous machines. Make sense? Okay. All right, so for the grad students, that's what you're going to be doing in D1 through D5. For the undergraduates, if you're running ahead and if you reach the end of assignment 10 early, before the end of the course, you're welcome to try and tackle the differentiable assignments if you want. This is new territory for this course, so if you do tackle the differentiable assignments and you get stuck, please come and see me during my office hours rather than the teaching assistant, and I will try and help you as best I can. Any questions about any of that? Okay, all right, undergraduates, I lost where we were here. Here we are. You are going to be tackling assignment 6 this week. In assignment 6, you're kind of pausing for a moment, and you're going to be doing a bunch of refactoring. Your code base through assignments 1 through 5 is getting larger and larger and larger, and I don't know about you, but at this point you've probably forgotten where variable XYZ is and where function ABC is. So you're going to refactor the code, modularize it, clean it up a little bit. So as you continue on through assignments 7, 8, 9, and 10, you'll have a more modular code base, and it'll be easier for you to remember where everything is, make improvements, rapidly debug anything when it goes wrong, and so on. Okay, all good? Okay. All right, back to our lecture material. So last time we just finished lecture 8, where we looked at a particular kind of neural network controller, the CTRNNs. CTRNN stands for? Thank you. Continuous time. So we're dealing with neurons that are changing their values continuously over time. CTRNNs have much more biological detail built into them than the standard neural networks we've been looking at so far. They're more complicated, but that complication buys us some things. It allows the evolutionary algorithm, makes it easier for the evolutionary algorithm to evolve behaviors for robots that are being controlled by a CTRNN. We ended last lecture by looking at this small humanoid robot that was shaking blocks up and down, and then left and right, and then forward and backwards. That robot evolved the ability to exhibit a particular building block of intelligence, which is the ability to stack hierarchically together motor primitives. Yeah? It was able to do that by having a CTRNN brain in which some of the neurons are quick and orchestrate sensor motor coordination, and then other neurons are slow and act like the conductor of a symphony, and slow changes in those slow neurons push the activity of the fast neurons into different motor primitives, push the fast neurons into different motor primitives like this, and like this. So some of that biological detail made it easier for the evolutionary algorithm to evolve hierarchical arrangement of motor primitives. Okay, so today we're going to push on to lecture 9, where we're going to look at the original minimal cognition experiments. As you'll see in a moment, the robots in these minimal cognition experiments, they look very much like Bradenberg vehicles. They're very, very simple. They're being, all of them are going to be controlled by CTRNNs, so they don't necessarily have minimal brains. The goal in the minimal cognition experiments is to try and evolve more and more and more and more of these building blocks of intelligence. If we can't define what intelligence is, why don't we sort of agree on the things that are necessary for intelligent behavior here in the real world and see how many of them we can evolve into machines, which ones are more difficult than others, how do we combine them together in a machine that is able to exhibit more and more and more of these building blocks. And maybe that's a more systematic way to approach the creation of increasingly intelligent, increasingly complex, increasingly useful, and increasingly safe machines. Very different from the dominant paradigm at the moment, which is make ChatGPT, release it to the world, and hope everybody finds a good use for it and that nothing bad goes wrong. You obviously know where my sympathies lie. I'll leave it up to you to form your own opinions. Okay, minimal cognition. Here we go. I hope you enjoyed today's lecture. You can think of it as like the Robot Olympics. We're going to look at a whole bunch of different events where the robots are going to be tasked with exhibiting we're going to look at 4 different building blocks today, 4 different competencies of intelligent behavior. Let's start with the first of the 4, which is perceiving affordances. We've seen a number of concepts from psychology make their way into robotics so far. Affordances is another big one. Anybody come across this concept in a psych class before? I'm sort of giving you the punchline here already. When we look about in the world around us, and I was to ask you, for example, to describe what a chair is, you'd probably give me a geometric description of a chair. It's got these vertical things underneath that are made of sufficiently strong material to hold up this flat piece, and there's usually a flat back, and you go and try and describe it. Back in the 1970s, when people were starting in on trying to get AI to recognize objects and what they're for, that's what they did. Programmers spent decades trying to describe to a computer what a chair is by giving it a geometric description, a geometric understanding of chairs. It doesn't take long to realize that a geometric approach to understanding objects runs amok, because this particular thing here, not strictly a chair, but it clearly belongs to this other group, breaks a lot of those geometric assumptions of what a chair is. I deliberately picked these 5 images because they clearly, hopefully to you, they all immediately have something in common, but I challenge you to find a geometric commonality among these 5 objects. It feels as if we understand objects in the world based on their geometric properties, but thinking about thinking is misleading. A concept that came out of psychology in the 1970s and the 1980s was an idea that when humans look at objects, we might think we're classifying our understanding objects based on their geometric properties, but we're actually understanding objects based on the affordances they project to us. We can imagine objects out in the world shouting at us about the ways in which we can interact with those objects. So an affordance that's shared by all of these objects for adult human beings is that they are sittable. You could rest your weight on them in a relatively comfortable manner. That description is about you, or about you and the interaction with the object, and what kind of interactions that object affords to you. That's the idea of affordances. What do these objects have in common? What about these objects? What do they have in common? We're playing the affordance game now. They all contain energy that's exploitable by us. It's always it's about us. The observer is a part of understanding the world around it. What we are doing as active entities in the world that want to survive and thrive in the world, we're selfish. We're looking at everything, thinking about how we can use it, how we can interact with it, how we can consume it, how it can make our lives a little bit easier, and so on. That's the idea of affordances. So maybe when we're trying to make smart computers and smart robots and smart machines, we should be trying to teach these machines to look at the world around them and not run computer graphics or try and recognize particular geometries like, does this thing have 3 or 4 vertical struts and a horizontal platform on top? They should be looking for affordances, trying to learn or evolve the ability to recognize how they can interact with objects out there in the world. Make sense? Okay. Optional homework as you continue on with your day today and you look at the myriad objects that you look at, watch yourself watching those objects, and you'll notice that on the surface it feels like you're recognizing things based on geometric properties, but you're really thinking about affordances. Writable, listenable, erasable, and so on. Okay. All right, so now let's have a look at trying to get a minimal machine to perceive affordances. Here's the first of the 4 minimal cognition experiments. As promised, we have a very, very minimal robot here. We've got a square, so this is a minimal physical simulator as well. Our little robot here exists in a 2-dimensional world. These 2 little horizontal axes here represent 2 rockets. So in our Bratenberg vehicle, we had 2 spinning wheels. I want you to now imagine a square with 2 opposing rockets, and those rockets can exert more or less thrust. If both rockets exert exactly the same thrust, the robot goes nowhere. If neither of the rockets emit thrust, the robot also doesn't go anywhere. If one emits more thrust than the other, it moves to the left, and vice versa, it moves to the right. So we've got a little Space Invaders type robot moving along the bottom of the screen, left and right, at different velocities and accelerations and decelerations. And from above, we're going to drop a pair of objects. Everybody still know what Space Invaders are? Okay, all right. All right, here we go. We're going to evaluate every CTRNN. We're going to drop CTRNNs into this minimal robot one after the other. We're going to evaluate each individual CTRNN's ability to produce behavior on average for the robot. So the first little bit of math here in the upper right, we're going to compute P, or the performance of the robot. This is synonymous with fitness. The authors of this paper just use P instead of F. For our purposes, it doesn't matter. And they're going to sum a whole bunch of P sub i's, which is the performance of a given CTRNN on the robot the ith time. We're going to take the average of how well that CTRNN causes the robot to do at whatever we want it to do, num trials time. So far, so good? Okay. In each of these num trials, we're going to drop a pair of objects from above. That pair of objects are going to fall at a constant rate, and the robot can sense this object pair. So the gray emanating lines here represent 1, 2, 3, 4, 5, 6, 7 proximity sensors on the front of the robot. So this should look pretty familiar. This robot has 7 proximity sensors, 2 motorized rocket thrusters, and a CTRNN inside. You'll notice that at this instant in time, this pair of falling objects is triggering the 2nd, 4th, and 5th proximity sensor. Those sensors are firing a little bit more strongly, and the 1st, 3rd, 6th, and 7th proximity sensor are returning a value of 0. Make sense? Okay. What is the robot supposed to do? As this pair of objects is falling, the robot has to figure out whether the pair of objects is passable. The robot is trying to recognize a particular affordance projected by this object pair, which is whether the robot, if it gets between the pair of falling objects, the pair of objects will fall on either side of the robot and not hit the robot. Is the object pair passable or not? Is this gap wide enough for the robot to pass through or not? That's the affordance we're going to try and evolve this robot to recognize. Okay, so how do we compute P sub I, how well the robot does given a particular CTRNN on the ith trial? We're going to consider 2 different cases. We're going to consider the case where the opening between the object pair is too narrow for the object to pass through. So let's imagine, actually you can see it in this cartoon here, this gap is narrower than the width of the robot. So in this case, we're going to set P sub I to a maximum value of 100 if the robot does not hit this object pair. This object pair is going to fall towards the ground, and the robot should be nowhere near this object pair when it gets to the ground. If it does that during the ith trial, 100 points. Otherwise, if it hits either of the pair of objects, we're going to assign P sub I T 2 times D sub I. D sub I is the final horizontal separation between the horizontal position of the robot and the horizontal position of the object pair when it gets to the ground. Horizontal distance between the robot and the object pair when it hits. There's a typo in the paper. They take the absolute value of the distance. Distance is always a positive number. Little typo there. Okay, so what is this particular term doing for the robot? What's the worst possible thing the robot can do in this case? The object pair is falling. The gap is too narrow for the robot to get between the object pair. What's the worst possible thing the robot can do?
Still try to get through the middle.
Get right underneath the object pair, whack the pair of objects, hits the agent, and we compute d sub I, which is the horizontal distance between the robot and the center of the object pair. In this hypothetical case, d sub I is 0. P sub I is set to 0, maximum penalty. The robot did the worst possible thing. So what is this particular term in the fitness function doing? It's rewarding for run away if the gap is too narrow. Everybody get the game so far? Okay. You can probably guess, even without parsing the math here, what this term is going to do. In the other case, in one of the ith trials, if the aperture, the gap between the object pair, is wide enough for the agent to pass through, it should get 100 points, the maximum score, if the robot is standing directly underneath the object pair, and the object pair passes right past the agent, and it's inside the gap. Maximum possible points. If the robot runs away when the gap is wide enough for it to pass through, minimum points, no points. If the robot collides with one or both of the objects as that object pair reaches the ground, we're going to set P sub I to this thing. What is this thing rewarding or penalizing for?
So the absolute worst thing is if it runs beyond blocks, so then it's rewarding for getting closer to the successfully going between blocks.
Yes, so the worst thing you can do is be beyond the blocks, that's 0. If you're pretty far away from the center of the object pair and you get hit, that's bad, and you're going to have a pretty big d sub I. So we've got a pretty big term on the minus side here. So we're trying to minimize d sub I. If the robot's not quite sure what to do and it's jittering back and forth underneath this object pair and it hits one or both of the objects, we're going to set P sub I to 80 minus this distance. We're trying to make this distance less and less and less. So we're trying to make everything on the right-hand side of this minus sign less and less and less if the robot's hitting the block, until eventually a robot evolves in which d sub I is small enough that, boom, it's not hitting either of the objects in the pair. It's staying right underneath and letting both objects pass on either side. So in this second case, when the aperture is passable, what is this conditional doing? What is it selecting for? When the aperture is too narrow, this selects for run away. When the aperture is wide enough, this term is selecting for going through, stay in the center, right? Be right in the center. Imagine we take one C-N, we drop it into the robot num trials times, and sometimes the object pair has a passable gap, sometimes the object pair has a non-passable gap. We're applying these two different fitness terms. We see how well it does at running away when the gap is impassable, and we see how well it's doing at get right underneath when the object width is passable. Sum all those up and take the average of all of those terms, and P should be high when the robot runs away when it should run away, and P should be high when it gets right underneath the pair when the gap is passable. Make sense? Okay. Let's see how it does. I apologize in the back of the room. I'll try and talk you through this axis. What we're looking at in this bottom left panel is the most fit CTRNN after the evolutionary algorithm has run. So the investigators have evolved a population of CTRNNs. In the first generation with random CTRNNs, P is probably pretty close to 0. The robot doesn't know what to do. And over evolutionary time, in this population of evolving CTRNNs, some of the CTRNNs start to achieve higher and higher average performance until at the end of several hundred generations, they have one CTRNN that gets a p-value very close to 100. They take that one evolved CTRNN, go back to the robot and drop it into that robot thousands of times under lots of different conditions. And they want to see how robust is that evolved CTRNN. How well really does it allow the robot to do at what we want it to do in this case? On the horizontal axis here, this is showing us that the investigators drop that CTRNN back into the robot thousands of times with varying aperture. Good to know my software is up to date. Thank you. Okay. Dropping that CTRNN back into the robot thousands of times with aperture widths that are wider and wider and wider than the robot's width, and apertures that are narrower, narrower, and narrower, and narrower. And in all of those different cases, they measured the robot's final horizontal separation. Where was the robot horizontally relative to the object pair when the object pair hit the ground? How does this CTRNN, this single evolved CTRNN, how well does it do in general? Well, yes, it's doing well. Is it doing perfectly? Not quite, right? Evolution is a satisficer, not an optimizer. How is it deviating from optimal behavior?
I'm guessing from looking at this that the robot is around like 40 units wide.
It doesn't actually show us that. So the 40 up here, this says that the robot was 40 horizontal units away from the object pair when the object pair hit the ground. Again, this is a unitless simulation, so it's not that doesn't really tell us much. You just have to trust me that 40 just means it's really far away from the object pair.
Well, we can tell on the plot that it's not perfect because like it doesn't immediately drop down to 0 when it begins like going in between both of the pairs, assuming that's like what it means when the final horizontal separation is around like 1 or like 1.5.
Actually 0 here, relative aperture width of 0. This represents a case where the width of the aperture between the pair of objects is exactly the same width as the robot.
Okay.
Make sense?
Yeah.
Go ahead.
So like when it drops down, it doesn't drop down to like immediately 0. It is just never able to reach like the point where it's perfectly between the blocks.
Absolutely. So there's something interesting going on here, right in the case where the width is just about passable.
Yeah, I can't like quite tell if it can fit or not, so it's like I should just go away because it might not be able to fit. Like,
Good point, right?
Do the same kind of thing too. It's like
yes.
if it's like life or death like that, you might be like, it's better to just run away.
It's better to run away, right? We're using very Bratenberg-esque language here, which is fine, right? Right when the aperture is a little bit wider than the robot. In theory, the robot can pass between the object pair. These big black vertical bars, these represent error bars or confidence intervals. What this means is that this evolved CTRNN saw lots of different falling object pairs in which the aperture was wide enough, and some of the time it ran away, and some of the times it took a deep breath and actually went for it and tried to get between the object pair. but it's being kind of conservative, right? Optimal behavior is this black dot should be right down here. If the aperture is passable, the robot is supposed to go for it, but it's not. It's being a little bit careful, and as you said, we tend to do that as well. So on average, maybe the best thing is to err on the side of caution. If you're not quite sure, run away. Kind of interesting, right? It's a non-optimal behavior. Humans and every other species on the planet, we are also not optimal, but the bias that we typically have kind of makes sense. The ways in which we're non-optimal sometimes are kind of a good thing, right? Kind of interesting to see that reflected here in an intelligent machine as well. Emily.
Do you think if they change the top function to be max of 0 rather than 100 minus 4d, that maybe it would be a little bit more risky?
Absolutely. Great point, right? So we could go back. If we saw this and said, yeah, we want this robot to be a little bit braver, we might be able to go back and alter the fitness function to exert a greater reward for going for it, regardless of how passable the aperture is. Or maybe we would punish with greater force cowardice, right? Running away when you shouldn't be running away. Interesting. Another piece of optional homework for you. See if you can sit down and try and rewrite these fitness functions that, at least in theory, would sort of clean up this conservatism here. Everybody see that? Question?
Yeah, how can we be sure that the behavior we're seeing around 0 is due to, sort of this potential cowardliness, instead of just like inaccuracies in the sensors, causing it to sometimes accurately guess will say that it can fit, where sometimes it thinks it can fit and it can't, just because of the data it's given.
That's a great point, and you're right. So what we're looking at is we're looking at a lot of data in this plot, but all that data is coming from one evolved CTRNN, and that one evolved CTRNN might have idiosyncrasies in it. We could take this evolutionary run, and instead of taking the CTRNN with the best fitness, we take the CTRNN that had the second best fitness. Maybe it's the brother or sister of this CTRNN, or a cousin or a second cousin. It's not quite the same. If we did the same thing to that CTRNN, would we get the same picture? Maybe we'd get a different picture. Maybe that one would be a little more brave, and maybe it would be foolhardy. Maybe it would try and run the gap when the gap is too narrow. Maybe there's an issue with the sensors. Maybe when that gap is just right at the edge of being passable, the robot can't tell. My understanding of this simulation is the robot actually can tell. The sensors itself, it's only ever getting 7 numbers at any one time, but remember that this robot is moving back and forth horizontally at the bottom of the screen. It's like cat whiskers. It's able to sweep its 7 proximity sensors across the undersides of the objects. This thing can actually sense very well and pick up very subtle details, and we'll see another example of that in a moment. So it's a good observation, but I doubt it's because of some limitation in the sensor motor behavior. Good point. Other questions or comments before we push on? Yes?
It's funny to me that as the width gets larger, it starts to it seems like maybe it cares a little bit less when it's directly at 0. It has more leeway, so it's like
it's showing off, right? The gap is really wide. It gets underneath, and it kind of
want to move or something.
Yeah, exactly. And again, I apologize. It would have been great to see some of the videos of these. Not quite clear exactly how this robot is moving. We're inferring its behavior by looking at this data. Okay. Let's actually dive in. Again, we don't have an actual video of this behavior, but let's actually investigate a little bit more about how these CTRNNs are evolving. I love this particular paper and I love this particular lecture because of these sort of different building blocks they look at. But these investigators really did their due diligence. As we're going to see, they really analyzed in great depth how good or how poorly these CTRNNs evolved. How well do they do in general? This was 23 years ago. This was, in my opinion, good work. This is something that we as a society are now struggling with. We have intelligent machines, and we're kind of deploying them out into the real world. And sometimes they generalize well, and sometimes they don't. How do we really know when we've got something that does well on paper and also will generalize well to many, many, many different situations in the real world, including edge cases, cases where it's going to be difficult for the machine to know whether to zig or zag. In this experiment, literally. Okay, here we go. Again, we're going to look at one good evolved CTRNN up here. Let's have a look at this. Upper left panel for a moment. What they're going to do in this case is they're going to take an object pair in which the gap is not passable. The robot can't get between the gap, and they're going to drop that. That object pair above and to the left of the robot. Then they're going to drop that same object pair above and above and to the left of the robot, but a little bit towards its center. They're going to drop that object pair from here, then 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 here. So each one of these black trajectories represents one trial. Everybody see that so far? Okay. The vertical axis here is representing the vertical position of the object pair. So as we descend this panel from the top to the left and watch one of these trajectories, we can see that pair of objects falling. The horizontal axis is representing the horizontal position of the robot. The horizontal position of the robot relative to the object pair. So let's start with this trajectory in the upper left. So at this point, the object pair was dropped 40 units to the robot's left. What did the robot do in that case? Follow this leftmost black trajectory from the upper left part of this panel. How did the robot move? If we follow this trajectory, it's more or less vertical, kind of vertical for a while. What is that telling us about the robot?
It's like just waiting.
It's waiting. The horizontal distance between the robot and the object pair is remaining at -40. The robot's moving a little bit, but not too much. And then it starts to move. Horizontal position starts to decrease towards 0. What is the robot doing? It's going towards the center. At least the robot is moving to the left. The object pair always falls perfectly vertically. I'm sorry, I forgot to mention that detail before. Object pair always falls perfectly vertically. The robot is starting to move to its left, and what happens after that point? The robot keeps going. It's a little hard to see in this plot. This trajectory continues down here, and this trajectory ends down here in the bottom right. What does that tell us about the state of the robot and the object pair when the object pair gets to the ground?
It's not under it.
It's not under it. It's where?
On the other side.
It's on the other side. The object pair started upper left. The robot started to move underneath it and just kept going, and the object pair fell 40 units to the robot's right. Okay, that's for one trial. Now tell me about all of these trials. What is the CTRNN causing the robot to do in all of these trials in which the gap is impassable?
It's causing it to move 40 feet away from like that central position.
40 feet away, 40 meters away, whatever it is. Sometimes to the object pair's left and sometimes to the object pair's right. It's always doing the right thing, right? Always running away. Everybody see that? Okay. Same evolved CTRNN. We're going to expose it to a whole bunch of other situations here. We're going to drop the object pair from different horizontal positions at the top of the screen, but in this case, the gap is just passable, just wide enough for the robot to thread its way between. What does the robot do in this case?
Goes through the gap.
Goes through the gap in every case.
It's interesting that it's like going back and forth through the middle ones.
You'll notice that if we drop the object pair towards the, more or less above the robot, it kind of goes a little bit to the left, and then a little bit to the right, and then back, and then stops and shows off, right? For the last third of the simulation, it just stands there and waits for either object to fall on either side of it.
Does that mean like the movement of it is helping it to judge the gap or something like that?
So this is what the robot did. Can we work backwards from its behavior in both situations to what it's thinking? Is it sweeping back and forth? So again, it's using its proximity sensors like cat whiskers to brush against the undersides of the objects to better understand whether the gap is passable or not.
I would guess that, at least for the closer ones, momentum just might have a play. It might just try to move too fast and it's trying to recorrect itself.
It could. I don't remember whether the physics engine contains momentum. It might. That might be part of the reason. It might just not be able to. Who knows? Maybe this sweeping back and forth under the object pair is useful. Maybe not. What else are you wondering about what's going on inside the CTRNN given these behaviors?
Sorry, this is actually slightly side question.
Sure.
But I was curious about, in the graph it says that they used a gap that's 1 unit larger and 1 unit smaller.
Yep.
Could be impressive or not that impressive depending on the size of the robot.
Yes, it's not clear from this caption. Is it a huge passable gap or a hugely impassable gap? It's not clear from this picture, from the caption.
It's interesting that it doesn't just like immediately go somewhere. Like
Yeah.
it does take some time, and it like does this oscillating or whatever, and then it like decides. Like maybe you would expect it to like just sense and judge and then just go where it needs to go, but it doesn't do that.
Absolutely, right? Again, there's evidence here of non-optimality. It seems to be taking its time. Again, that's due to the fitness function. The fitness function contains d sub I, remember, which is the horizontal distance between the robot and the object pair when the object pair hits the ground. There is nothing in the fitness function that says figure it out quickly. Just do the right thing when you need to. That's it. So, not surprisingly, the robot seems to be taking its time.
You could have some term or something in there that like punished it for using more energy or something like that.
Absolutely, you could. Yep. What else can you infer about the behavior of this robot? It's minimal, it's very simple, but even in the simple case, there's a lot of rich dynamics that are going on here. Lots of aspects of its evolved behavior that suggests things that might be going on inside the CTRNN.
Well, it's just interesting that it seems to behave the same exact way, whether it's to the left or the right.
Ah, yes.
So I'm wondering, yeah, like I feel like I remember you saying usually the weights like aren't symmetrical when we evolve, but it appears that maybe they are in this case.
Great observation. If you look at both panels, each panel is bilaterally symmetric. The left side of the panel looks like the right side of the panel, which means that the robot seems to be exhibiting exactly the same way of moving and ultimately what it does in whether the objects are top left or top right, which suggests the synapses inside the CTRNN have evolved to be bilaterally symmetric. And I can tell you that the researchers did not put that in this case. So this is probably the evolution of bilaterally symmetric behavior. Good observation.
For the left one, you can see there are like certain trajectories that get further away faster, which is interesting. It looks like it's maybe like the ones that are closer to the middle versus like all the other ones, but the farther out ones take a little bit longer.
Absolutely.
Maybe that is indicating something about how it's like sensing the gap or something.
Could
I
be.
don't know, but it's just interesting that there's like pretty much all of the ones in the middle seems to like hit this one trajectory, and then the ones on the outside.
Absolutely. So it looks like in some cases it's taking the robot longer to decide what to do. When does the robot know? When does it decide the gap is too narrow, I'm going to run away? Or when does the robot decide the gap is wide enough, I'm going to go for it? When?
Seems to be around like when the gap is at vertical position 60-ish.
It looks like it, right? If we look at both panels above 60, those two pair of trajectories look almost identical, right? So the robot seems to be doing exactly the same thing when the object pair is above that height, regardless of whether the gap is passable or impassable. Looks like the robot doesn't know until 60, and then it looks like at a height of 60, the robot decides and either runs away or gets right underneath the object. It's obvious. The robot is making the decision at a height of 60. I see some of you smiling. You should know by now in this course, whenever I say it's obvious, that it's not. The robot is acting as if it decided at that point. Never know, right? You remember the Libet experiments? Human subjects said, I know, I decided at this particular time point to twitch my finger. They thought that they were wrong, right? Hard to know, actually, when this robot decides or how it decides. But it does decide. There's something that's triggering run away or stay where you are, or at least get underneath the pair. All good? Okay, let's keep going. These investigators really were interested in detail. Let's talk about the lower left panel now. You'll notice that it's a whole bunch of differently colored pixels, white, gray, and black pixels. Each individual pixel in this panel represents a single drop of an object pair. Pixels that are pixels in the upper half of this panel represent object pair drops in which the gap was passable. Pixels in the lower half of this panel represent drops of the object pair in which the gap was not passable. Pixels to the left of this panel represent object pairs that were dropped up and to the left of the robot, and pixels to the right-hand side in this panel represent pair drops, pairs that were dropped up and to the right of the robot. So far, so good? Okay. For each of those conditions, the investigators colored that pixel white if the robot did the right thing, black if the robot did the wrong thing, and gray if it kind of did okay. Maybe it was jittering around, maybe it bumped one or both of the objects. Tell me about, again, this single evolved CTRNN. What is it causing the robot to do in thousands of different situations now?
It has trouble like on the sides with horizontal positions that are close to the edge, which is interesting.
Okay, you're talking about these big gray blobs up here?
Yeah.
You're right. So these are far to the left and far to the right, which represent cases where the objects were dropped far to the left or far to the right of the robot. And all these gray blobs are in the upper half, which means
That it could go through.
the aperture was passable.
Yeah.
It could go through, but it was bumping the blocks in this case. It wasn't quite sure what to do.
It does especially bad when you just put it right above it. Sorry.
If you drop the object pair directly above the robot, it does really poorly when the aperture is passable. It runs away. Down here, when the gap is narrow, it also runs away, which in that case is the right thing to do. Why do you think it does so terribly right when the object pair is dropped directly overhead? Seems kind of odd.
If you look at the graphs above, it needs some sort of motion to detect
or like to make its decision
May-
on what the block, like whether it needs to go in or not?
Maybe. So it looks like the robot needs to move back and forth to determine whether the gap is passable or not. But the object pair is dropped from directly ahead. It's still free to move back and forth and figure it out. It doesn't seem to be able to figure it out in a lot of these cases. What gives?
When an object's like directly above you, like it's the hardest to perceive like distance between both the objects.
Maybe. In that case, the robot should just move left and right, figure it out, right? Don't have the object pair be directly above you. The robot's free to move back and forth.
I assume that maybe because the network developed completely symmetrically, then if maybe one side is triggered, maybe on one side and the side of the network is triggered, maybe on the other side, then there's competition when both sides are activated by something.
Could be. Maybe there's something about the symmetry that helps it in general, but there are specific cases in which it kind of, it's fighting with itself, possibly. Another hint is if you look at this picture, you'll notice that they never actually dropped the object pair from directly overhead. Now, this was an experiment they performed after evolution, but my guess is, and they don't explicitly say it in the paper, is that during evolution, they also never dropped an object pair directly above the robot. It just never saw that situation. Again, it's not clear. It might be a little bit of all of these explanations. This is a hallmark, unfortunately, of every intelligent machine on the planet at the moment, right? Robot, ChatGPT, Stable Diffusion. In general, they work pretty well. Most of the pixels in this plot are white. Great. Unfortunately, there are regions or there are situations in which not only does the machine kind of misbehave, it does absolutely the wrong thing. And in this minimal experiment, we can actually sweep over all possible conditions, or almost all possible conditions, and see where those blind spots are in the machine. Unfortunately, here in the real world, harder to do. No one has an answer about how to deal with this problem or make it better. Plenty of people in the community will tell you that they do. No one's figured it out yet. Hopefully some of you will help with this very needed solution. Okay, shall we push on? Okay, that's competency number 1, perceiving affordances. We just saw an evolved robot that's able to tell you or show you that it knows whether a gap is passable or not. Let's look at the second of 4 building blocks of intelligence that we're going to look at in the minimal cognition experiments. This one is discriminating between self and non-self. We've actually already seen a robot in this course that learned to do this. What was that robot? Anybody remember? You forget his name, her name? What did Babybot, right? The 2 cameras, all it could see was whether things move or not when it sends commands to its motors. Very important thing for machines and tiny humans to figure out as well. Figure out where you end and everything else begins. Okay, so characteristically, the investigators investigated the ability to evolve self, non-self discrimination in a minimal robot. This robot is welded at the bottom center of the screen. It has no rockets. It can't move left and right, but it has an arm pointing up in front of it, and it can send commands to rotate this arm backwards and forwards above its head. And it's got a little tiny hand which self-occludes its vision. So again, this robot has 7 outgoing proximity sensors, and you'll notice that 2 of them are being blocked by its hand. It's actually seeing its own hand. Everybody see that? At the same time that this robot is seeing its own hand, it is also seeing a single object that's falling from above, and the dashed arrow here is telling us that this object can fall at different angles towards the bottom of the screen. It can fall at different velocities. From the robot's point of view, all it knows is that its second, third, and seventh proximity sensor are chirping, and the other 4 proximity sensors are at 0. How does the robot know which of these is self and which of these is non-self? Seems easy, right? The object that's really far away, that's probably non-self, and the thing that's really close is probably self. Easy now, but as this object continues to fall and touches this imaginary arc here, now it's seeing self and it's seeing non-self, which is equally close to it. How does it know which is which? Not so easy. Yeah? Okay. How did the investigators evolve self-non-self discrimination? They're going to rerun the experiment they just did before. They made a few changes to the robot and a little bit to its task environment. The underlying evolutionary algorithm stays exactly the same. They're going to evolve populations of CTRNNs, but they're also going to change the fitness function. The fitness function is still going to compute P for each CTRNN in the population, its average ability over a bunch of object drops. For the ith object drop, they're going to compute the performance of the CTRNN during that ith object drop, and they're going to compute it using this equation. Again, there's a typo in the paper where it says max, it should be min. You'll see that on the right-hand side of this equal sign, there is only one variable, theta sub I, and theta sub I is the angular error at the end of the ith trial. The trial ends when this object touches this imaginary arc. And at that point, they look at the angle of the object relative to the robot. So if this black sphere hits here, this would be an angle of whatever that is, minus pi over 8 radians. And the angle of the arm. In this case, it looks like it's minus pi over 16 radians, more or less. Theta is going to take the error between those two angles. What is this fitness term doing? What is it trying to evolve CTRNNs to do? Catch the ball, right? Theta, if you ignore all the other machinery in this term, theta is on the right-hand side of the minus sign. So they're trying to if this error is always a positive value, which it is because it's inside absolute bars. They're trying to make this error minimal, which is the robot should catch the object. Its little hand should be exactly where the object is when the object hits this imaginary arc. So far, so good? Okay. All right, evolve, and at the end of evolution, they pluck out the CTRNN that has the highest p-value, the most fit CTRNN, and then they drop that CTRNN back into this little robot over and over and over again under a whole bunch of different conditions. Let's look at these conditions. On the horizontal axis here, they're reporting final object error. So this is the angle at which the object hits this imaginary arc. Minus values, the left-hand part of this panel represents objects that hit above and to the left of the robot, and the right-hand side of this panel corresponds to objects that fall and hit the right-hand side of the robot. The vertical axis represents the angle of the arm when those situations occur. Tell me about the behavior of this robot when it's armed with this CTRNN. How does it do?
Kind of does the same thing as the last robot, where when it's like 0, 0, the error is greater than all the other cases around it.
Okay, so when the object falls and hits right above the robot, the error bars are a little bit taller here, representing there's a little bit more variation in its behavior. Sometimes when that object hits directly ahead, sometimes the arm is a little bit to the left. And sometimes when that object hits directly overhead, the arm is a little bit to the right. So it's a little unsure. But generally speaking, how does the robot do? It's good, right? It's not optimal. Again, what would optimal behavior here look like? No error. You see this dashed gray line underneath? That's what it should be doing, right? The angle of its arm should always be exactly the angle at which the object hits the imaginary arc. Good, not perfect. Okay, here we go. This is arguably the most difficult panel to parse. So deep breath. We'll take it a little bit at a time. Same thing, we're looking at the behavior produced by one CTRNN when we drop that one CTRNN sequentially into the robot. Some cases, let's see. Let's start with the colors here. So dark trajectories here correspond to cases in which, let me make sure I get this right. Okay. Trajectories are shaded according to the initial angular position of the object. So black trajectories over here, which you can't see because they're underneath this light trajectory. Dark trajectories over here correspond to the object being dropped above and to the left. Lightly colored trajectories correspond to objects being dropped above and to the right of the robot. The actual position of the trajectory corresponds to the angle of the robot's arm. So all of the trajectories that start up here to the left, this is the investigators taking the robot's arm and cranking it to the left just before the simulation begins. And then when the simulation begins, they let the CTRNN control the arm. All the trajectories that start bunched up here in the upper right, those are cases in which the investigators cranked the robot's arm to plus pi/8 radians, and then when the simulation starts, they let the CTRNN control the arm. Light gray trajectories that start to the left meaning the robot's arm was cranked to the left, but light trajectories mean the robot's arm is to the left and the object drops from upper right. Get it? Black trajectories to the left here. The trajectories to the left, object is cranked to the left. The trajectories are black. The object starts falling from upper left. Can you parse the rest of this figure? What's happening? The horizontal position of the trajectory at any point in time represents the angle of the arm during the simulation. What's happening?
Doing a lot of sweeping.
Absolutely. Whatever else is going on, in every case, it's doing a lot of this. What else can you tell me about what this robot does under these conditions? What does it do at the end when the object gets to the robot? What's happening? There's 4 different initial conditions. Arm cranked to the left, drop the object from upper left or upper right. Crank the arm to the right, drop the object from upper left or upper right. 4 different initial conditions. What happens in all these cases?
The arm ends up pointing up.
Absolutely. At the end, down here, all of these trajectories are at an angle of 0. The robot is holding its hand directly overhead. We know that this particular evolved CTRNN more or less does the right thing under most conditions. So where do you think the object is hitting, regardless of whether it's dropped from upper left or upper right?
In the middle of the arc.
In the middle of the arc, right? It's catching, in every case, the CTRNN is enabling the robot to catch the object, more or less. There's a little bit of uncertainty here, but it's mostly doing the right thing. How? How is it catching the object?
It's like tracking it as it's coming down and sweeping across it, and then as it comes like down, it looks like it catches it like at that time.
Absolutely.
Yeah, you can see like when it's on the other side, it goes all the way over, and then it tracks it down, and then.
You're talking about these trajectories. They
Yeah,
start over here.
they're interesting.
Exactly. So let's follow one. It's up here to the right, meaning the object was dropped, upper right, and the arm goes like this. And then if we follow this trajectory over here, the arm is going all the way over to the left, and we're following a dark trajectory. Sorry, I misspoke. Sorry. If we follow a dark trajectory from upper right, if it's a dark trajectory, that means the object was dropped from upper left, but the arm was cranked all the way to the right. The object starts to fall, the arm overshoots, and then as this object is falling from upper left, the robot is showing off, right? It's sweeping its arm back and forth. It's basically pointing to where it's going to capture the object. It's pulling a Babe Ruth here, right? Saying, I know, over here.
It's like, it seems like it figures out pretty quickly where the other thing is. Like, you can see that it sweeps over to the under the ball. Like,
It seems
pretty
to
quickly.
know pretty quickly where the object is.
It makes sense because it's a different size than its arm. So if it knows, the ball CPR then knows like, okay, at this point, yeah, I kind of know where my arm is. Like, okay, yeah.
Good point. Does it know that? Does it know that its hand is smaller than the falling object? We know it because we're looking at this JPEG. It only gets 7 numbers. At any instant in time, it's only ever got 1 number. Does it know? Is it easy for this robot because it knows its hand is small and the falling object is big?
And presumably it has learned that.
Maybe it's learned that. Remember the gantry robot, which was able to distinguish between triangles and rectangles? It learned or it evolved the ability to distinguish between those two shapes through movement. Probably the same thing is going on here. It looks like this is a relatively easy task for the robot to solve. So far, so good? Okay, let's keep going. We've got 5 minutes left, so we should be able to tackle the third of the 4th competencies. This one is short-term memory. If you, an organism or a machine, cannot remember anything from your past, there's only so many things you can do. You're pretty fragile, right? Definitely an important building block of intelligence is memory. So how do we evolve a robot to remember stuff? We've already seen some robots like the gantry robot that does evolve the ability to remember stuff. Let's have a look at another example. Okay, we're back to our Space Invaders robot now. It's got 2 rocket thrusters underneath. It's moving back and forth along the bottom of the screen. It's got 7 proximity sensors like before, but now they're being drawn with dashed lines, which is a visual representation of an additional detail they built into this experiment, which is that the robot is able to see, but the moment that the robot starts moving, all 7 proximity sensors turn off. It goes blind. So this robot cannot move and sense at the same time. It's being forced to sense and then to, quote unquote, choose to act. And the moment it chooses to act, no more sensory information. They're going to drop single objects from the top of the screen, and those single objects are going to fall at different angles towards the bottom of the screen, and they might fall at faster or slower velocities. You can probably guess what the robot is supposed to do in these cases. What's the robot supposed to do in this particular event? Get hit by the ball. Go catch the ball. Catch the ball, yeah? So you're the robot, you're standing motionless, you're watching the object fall from above. You make a decision, you go blind, and you start moving to make sure you're there when you catch it. This is a very simple fitness function. We've got d sub I on the right-hand side of the minus sign, which is telling us what? Are they rewarded? Is evolution rewarding for d sub I or penalizing for d sub I? Penalizing. We want to minimize d sub I. D sub I is the horizontal distance between the robot and the object when it hits the bottom of the screen. Pretty simple, right? Minimize that distance. Catch the object. Okay, here we go. Evolve, 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 evolve. At the end of the evolutionary algorithm, pluck out of the population of evolved CTRNNs the one that has highest fitness and drop that CTRNN repeatedly back into the robot under a whole bunch of different conditions. What are those different conditions? They're going to drop the object so that it hits the ground at different horizontal positions. In these cases over here, the object is going to hit bottom left part of the screen. Over here, the object is going to hit the bottom right side of the screen. And for all of those cases, the vertical axis is telling us where the robot was when that happened. The robot was either at the left part of the screen, at the bottom center of the screen, or at the lower right part of the screen. How does the robot do? Well, but not perfect, again, right? And for some reason, it seems to be having a particularly hard time with objects that are hitting the midpoint of the bottom of the screen. Why? Who knows? Okay. I think we'll end with this plot today. Same evolved CTRNN. We're going to put it back in the robot a whole bunch of times. We're going to start dropping the objects. And again, the horizontal axis here is now going to represent where was the robot when the object hit the ground. Bottom center, bottom left, or bottom right. The vertical axis, sorry, I misspoke. Horizontal axis is representing the difference between the robot and the object's position when the object hits the ground. Minus 40 means the object hit 40 units to the left of the robot. Plus 40 means the object hit 40 units to the right of the robot. In most of the cases here, you can see the robot did more or less the right thing. It was directly underneath the object when the object hit the ground. Vertical axis here represents the height of the robot and the horizontal difference between the robot's position and the object's position. You'll notice that for a while, almost all of these trajectories are perfectly vertical. What does that mean? What does that tell us about the robot's behavior? The robot is not moving. The object is placed 20 degrees above, or is placed 20 units to the left of the robot at the top of the screen. That object starts falling, and that horizontal difference doesn't change. Then it does start changing. When the trajectory deviates from vertical, what's happening?
It's like acting upon its prediction of where the other object is eventually going to fall.
It's acting on its prediction, right? It starts moving, which means it's blind at that point. How does it move? Continuously. There's no shaking left and right anymore. It's constant movement at a constant velocity until it catches the object. Why?
Because it is like, it's not trying to change for like what the later positions of the other like object is. So the robot just decides like it's going to go to this place and it starts heading there, and there's no other information to make it like swing back and forth and scan the area.
It doesn't need to sweep back and forth because it's blind. It can't see anything, right? Its cat whiskers have been cut, which suggests that in these other experiments, it was actually probably useful to be doing this, right?
So if it's moving at a constant rate, then it's blind the whole time that it's moving
It's blind the whole time it's moving. All of these times in which these trajectories are non-vertical, the robot is moving and it's blind.
It has short-term memory.
It has short-term memory. It knows. The moment it starts moving, starts moving at a constant velocity, and it knows that that velocity is going to get it right to the object, right when the object gets there.
So does that mean that like one of its neurons or some of them evolved to have like those longer, like we were looking at how those researchers had some neurons that have like longer longer term behavior versus like shorter behavior?
The time constant.
Yeah, time constant.
Maybe the CTRNN has tuned the speed of response of some of the neurons to produce this slow stroll at a constant rate to get there. Maybe. There's a couple of other details in this plot about the behavior of this robot. We'll save that for next time. You have a quiz due tonight. Grads, you're starting work on D1. Undergrads, you're working on A6. See you all on Thursday.